Okay, we are going to continue our discussion on arc length, and we are going to also talk about what angular speed is, how it relates to arc length, and we'll also incorporate a little bit of physics in there as well today. Okay, so let's start by talking about arc length. So an arc that has a central angle measure theta radians has length L equals R times theta. Okay, what that means is that the arc length is the radius, R, times the radian measure of the central angle of the arc. Okay, so visually what that means, we've talked about arc length already a little bit before, but say you have an angle measure here and you have a radius of R that's given to you. To figure out what that arc length is, all you need to do is multiply the radius times theta, but now note that this theta here that we do have is in radians. So note that this is actually the same exact formula that you had written last time, but instead of writing it in terms of degree measures, we are multiplying by theta, which is the angle measure in radians. Okay, so R times theta gives you the arc length. Okay, so take a look at example 1. It says the second hand on a clock is 6 inches long. How far does the tip of the second hand move in 15 seconds? Okay, so we have, we want to think about 15 seconds in terms of how far along the circle has it moved. So recall that the second hand on a clock is going to make a full rotation or full revolution every 60 seconds. So 15 seconds is a fourth of that revolution. Okay, so that means how many radians will it have moved? Well, think of it this way. One full revolution, if you remember, is 2 pi radians. If it only moves a fourth of the way, we can just do 1/4 times 2 pi to get us pi over 2 radians. Okay, so we do need to have this in radians before we can actually apply that formula, arc length equals R times theta, because theta is the angle measure, but in radians. Okay, so now we have that labeled, that's pi over 2. So now we are trying to find how far the tip of the second hand moves. So the tip of the second hand is really going to move exactly the arc length, right? The second hand is 6 inches long, that gives us the radius. So the arc length is equal to R times theta. And we know that the radius is 6 and theta is pi over 2. So just multiply that, we get that's equal to 3 pi, which comes out to be about 9.4 inches or so. Now, last lesson I had said when you're working in radians, you should keep it in terms of pi. Now, we did keep it in terms of pi, but then once we're trying to find the arc length, we're actually trying to find a measure. It'll be much easier to express it as, for example, 9.4 is something that's more tangible than 3 times pi, right? 3 times pi, you're still kind of thinking, well, how far exactly is that? You still have to multiply that. So go ahead and feel free to multiply that out. So 9.4 inches. Okay, let's look at example 2. Find the central angle measure in radians of an arc of length 5 centimeters on a circle with radius of 3 centimeters. Okay, so again, we're going to use that the arc length is equal to R times theta. Now, theta, remember, is the angle measure in radians, which is exactly what this is asking for, right? Find the central angle measure. Now it says the arc has a length of 5 centimeters, and the circle that it's on has a radius of 3 centimeters. So actually for this one, we have a picture for those of you who are more visual. We really already have L, the arc length. We have R, the radius, and we just need to solve for theta. Okay, so take L equals R times theta, plug in what you do know. So 5 equals 3 times theta, and solve for theta. So divide both sides by 3, so we have 5/3 radians. So it's not necessarily the case that radians will always be in terms of pi. Radians can be any measurement, but usually when we're talking about those specific angle measures from the ones on the unit circle, that spiderweb looking thing we did last time, all of those we want to keep in terms of pi. But it's not always that radians has to be in terms of pi, right? So for example here, 5/3 radians. So that just means that that angle measure, right, that's given there, that's 5/3 radians. And we know that 1 radian is equal to 180 over pi. If you were to divide that out, you get about 57 degrees. Again, we're trying to work our way into using just radians and not needing to necessarily convert back and forth between radians and degrees. Okay, now we're going to move on to linear and angular speed. So suppose that you have a wheel and it's rotating at some constant rate. So it's not going any faster or slowing down at all. It's just going around. It's rotating at a very constant rate. The center is at O there, and P is a point on the outer edge of the wheel. Now there are 2 ways that we can measure the speed of point P. One in terms of the distance that that point travels. The second is in terms of the angle through which it rotates. So the first is what we call the linear speed, the distance that it travels. The second is the angular speed, so the rotation through which it goes through. Okay, so let's talk about some formulas. So linear speed is the arc length, right? So it's really the distance that it travels. So normally that would be the circumference, but maybe it's not a full circle. Maybe it's just part of the circle. So that's the arc length. So that's the arc length, and since we're talking about speed, it's a distance over time. So arc length over time. So that would be r times theta over t. And then the angular speed is given by the angle that it goes through over time. So again, it's a speed, so it has to be over time. So that's just theta over t. Now, if you compare these 2 formulas, you'll notice that they're very, very close. The only difference is that the linear speed, you have to multiply by the radius r. So if we want to relate the linear speed to the angular speed, the linear speed is equal to r, the radius, times angular speed, right? That's exactly what we already have there. But so that you can see the relationship between the 2, it's related by the radius. Okay, we're going to take a look at this last example here. It says a merry-go-round makes 8 revolutions per minute. What is the angular speed of the merry-go-round in radians per minute? And then how fast is a horse that is 12 feet from the center traveling? And how fast is a horse that is 4 feet from the center traveling? All right, let's start with the angular speed. So first we want to think about what angle measure does this merry-go-round go through in 8 revolutions. Okay, now remember, we want to think about this in terms of radians. I know we're very used to thinking about everything in degrees up to this point, but let's try to avoid thinking of it as 360 degrees as 1 revolution. So remember, 1 full revolution is equal to 2 pi radians. So if it makes 8 revolutions in 1 minute, what radian measure has it gone through? Well, it's done 2 pi and then 2 pi and then 2 pi, right? It does that 8 times. So we can simply multiply 8 times 2 pi, and that gives us 16 pi radians in 1 minute. Okay, so that's the angular speed, right? 16 pi over, that's 1 minute, so this is 16 pi radians per minute. Okay, now parts B and C refer to the linear speed. So now that you found the angular speed, this actually makes finding the linear speed much easier, right? Once you have the angular speed, remember that the angular speed is related to the linear speed. All you have to do is multiply by the radius. So a horse that is 12 feet from the center means that it is 12 feet from the center of the circle, if you want to think of it, that merry-go-round as a circle. If it's 12 feet from the center, that means the radius is 12. So all you have to do is, to find the linear speed, is to multiply the angular speed, which you found in part A, and multiply it by r. So this is going to be 12 times 16 pi. And again, you can feel free to multiply this out, get an estimate answer. So this comes out to be 192 pi feet per minute. And you can actually leave it that way. You can multiply it out by pi if you'd like. Now, feet per minute is a little bit harder to grasp. We are probably more used to, say, miles per hour. So just a couple of conversions, knowing that there are 5,280 feet in 1 mile, knowing that there are 60 minutes in an hour, we can easily convert this and we'll have 6.9 miles per hour. All right, last part C. How fast is a horse 4 feet from the center traveling? So this is pretty similar to part B, but it's good to do out, and we'll also compare it to our answer in part B. Okay, so all we have to do is multiply the radius, which is now 4, by 16 pi. That gives us 64 pi feet per minute. And again, we're not as used to thinking about things in feet per minute for speed. So a few conversions into feet into miles and minutes to hours, we'll end up with this being about 2.3 miles per hour. Okay, so comparing this to part B, in part B, you were 12 feet away from the center and you traveled about 6.9 miles per hour. If you were closer to the center, we found that you travel about 2.3 miles per hour. So you kind of have an idea, at least in terms of linear speed, exactly how fast you're going, right? So linear speed, the closer you are to the center, the slower your linear speed is. The further away you are, the faster your linear speed is. But if you think about the angular speed, no matter where you are, if you're closer or if you're further away, that does not affect your angular speed. The entire merry-go-round is still going. It's still rotating 8 revolutions per minute, right? It's still rotating 16 pi radians per minute. All right, and that's all we have for today.